Outside, in the extreme summer heat, temperatures can reach 46 degrees Celsius. But step through a heavy glass door, and you are immediately hit by a wall of artificial winter. That sudden, effortless cold has built Dubai's ultimate luxury cooling empire. But maintaining this freezing illusion is secretly becoming a massive trap. To keep the desert out, air conditioning swallows roughly 60% of the city's peak power. Behind every frozen hotel room is a hidden industrial giant operating in overdrive. Another Dubai that tourists rarely see. And as the temperatures keep rising, this hidden electrical city is forced to expand, pushing the entire power grid to its absolute breaking point. How did the desert's greatest luxury turn into an inescapable power grid trap? Look up at the air conditioning vent in any luxury space in the city. Air conditioning does not actually make heat disappear into nothing. It simply moves thermal energy away from one enclosed area and rejects it somewhere else. Trace that cold air backward, and you will find a heat exchanger hidden in the ceiling. Follow the chilled water pipes leaving that exchanger, and you will find heavy industrial pumps in a mechanical room. Keep following the system out of the building, and you eventually reach a massive array of rooftop chillers. Those chillers require electricity to run their heavy compressors, which means they are physically tethered to underground cables, heavy transformers, and a vast power transmission network. The defining feature of a luxury interior in this environment is not the imported marble on the floor. It is the sheer volume of heavy machinery that must completely disappear from sight before the room feels effortless. Follow the electrical cables far enough, and the skyline begins to look very different. Tourists photograph the gleaming glass towers rising above the desert sand, but the electrical system has to prepare for the massive thermal loads those same towers create. Every visible architectural expansion above ground produces another invisible infrastructure requirement behind it. In July 2026, the Dubai Electricity and Water Authority reported more than 10 billion dirhams in strategic electricity transmission investments. That included 65 new 132 kilovolt substations currently under construction. This massive capital deployment is not evidence of a failing power grid or technical incompetence. It is evidence of an urban model that requires a continuously expanding electrical city just to sustain the visible one. The skyline does not grow alone. Whenever a new luxury development is announced, the transmission network must reach it, power it, and guarantee its climate control. It requires moving heavy transformers down highways, laying miles of underground high-voltage cables, and constructing concrete substations to step down the power. These heavy industrial installations are the mandatory anchor points for every new neighborhood. Why does a city famous for its limitless wealth and spectacular construction need its invisible electrical infrastructure to keep expanding at this scale? The answer lies in the way millions of indoor spaces consume power at the exact same time. The core vulnerability is not merely that air conditioners consume a lot of electricity. A much deeper engineering challenge occurs because thousands of buildings experience the exact same solar heat simultaneously. As the sun rises and pushes toward midday, thermal energy builds up against millions of square meters of glass facades. Inside those buildings, mechanical cooling systems must activate and work harder to fight the rising temperature. Historically, the critical summer peak load hours concentrate roughly from midday through the late afternoon. Millions of climate-controlled spaces demand intensive cooling during roughly the same dangerous thermal window. It is a massive synchronization problem that puts intense pressure on the grid. Think of a highly engineered urban highway system. A road can be completely empty at 3 a.m. and still suffer total gridlock during the evening rush hour. Electricity infrastructure must be built and maintained to survive those critical afternoon peaks. not just the average daily consumption. Every single transformer and cable must be sized to survive the moment when the entire city demands cooling at once. If the system cannot deliver during the hottest hours, the average capacity during the night simply does not matter. This synchronization forces engineers to design the system for the worst possible hour of the worst possible day. Watch a new skyscraper rise floor by floor above the financial district. As the concrete core goes up and the glass panels are attached, the city is not just adding square meters of real estate. It is adding apartments, hotel rooms, retail corridors, and grand lobbies that are expected to remain entirely usable through August. Every single climate-controlled floor makes the exact same physical promise to its occupants. No matter how hostile the outdoor temperature becomes, the indoor environment must remain perfectly comfortable and uninterrupted. A real estate developer looks at a new tower and sees profitable, rentable floor area. A tourist looks at that exact same building and sees architectural luxury. The electricity system looks at it and sees another permanent future summer load. Every pane of glass represents a thermal zone that must be mechanically defended against the desert heat. Every new square meter requires a continuous flow of chilled water, and that water requires continuous power. Dubai does not merely add space, it adds obligations. The grid must adopt the responsibility of keeping that space cool forever. This creates an uncomfortable reality for the engineers managing the grid. The problem becomes significantly more difficult when the amount of electricity required at the peak does not stay still. The infrastructure must constantly chase a rising ceiling of power consumption. In 2025, Dubai recorded an annual peak power demand of approximately 11.39 gigawatts. That figure represented an increase of roughly 5.83% compared to the previous year. The absolute gigawatt number demonstrates the sheer scale of the electrical energy required to keep the city running. But the percentage increase is far more important to the narrative of the infrastructure. It proves that the maximum thermal target the system must be ready to serve moved upward yet again. The disturbing part of this equation is not simply the massive size of the total demand. The disturbing part is that the finish line keeps moving further away while the construction cranes keep operating in the background. The power system must continuously expand just to prevent the existing city from overheating. Engineers cannot just build enough capacity for today and stop. They have to project how much power the new construction will require next summer and build the transmission lines to match it. But just as the pressure seems insurmountable, the city reveals a smarter solution. Instead of relying on isolated machines, Dubai has deployed a highly engineered alternative to fight the heat. Instead of forcing every single glass building to fight the extreme heat independently, engineers built massive centralized cooling plants. Inside these modern industrial facilities, heavy machinery chills massive volumes of water. That cold water is then pumped through a vast underground network of highly insulated blue pipes. It travels directly into multiple high-rise towers, luxury hotels, and entire residential districts at the exact same time. This is district cooling. It replaces thousands of individual rooftop air conditioners with one highly optimized, centralized industrial system. The centralized plants run more efficiently, require less maintenance space inside the towers, and use advanced control rooms to monitor thermal loads across entire neighborhoods. It is a highly engineered approach to managing the desert climate at scale. It sounds like an absolute escape from the heat. But district cooling is only a highly effective way to make climate control more efficient. It does not actually eliminate the fundamental requirement for cooling. It simply centralizes and industrializes that dependency. Efficient dependence is still dependence. By shifting the thermal load from individual buildings to massive central plants, Dubai has not removed air conditioning from the equation. It has permanently transformed cooling into a city-scale piece of heavy infrastructure. The luxury cooling system is no longer just a collection of commercial appliances hidden on a roof. It is an integrated urban system operating on the exact same scale as the water supply or the transportation grid. And because these massive central plants serve entire districts simultaneously, their continuous operation is absolutely non-negotiable. If a single rooftop unit fails, one building gets uncomfortable. If a district cooling plant loses its electrical supply, an entire neighborhood immediately begins to heat up. The efficiency of the district cooling network means the city can support even more massive developments without overloading the local grid as quickly. But that exact same efficiency ties hundreds of buildings to a single critical node. The city has built an incredibly sophisticated mechanism to fight the desert. But the efficiency of that system masks the reality of how deeply the urban environment relies on it. Up until this point, extreme heat has only been viewed as a problem for the demand side of the grid. The rising temperature forces buildings to consume more power. But extreme heat, simultaneously, creates a completely different physical threat. It creates highly hostile operating conditions for the energy infrastructure itself. Every electrical system on Earth experiences greater stress when the ambient temperature rises. Heat waves force generation plants, heavy transformers, and high-voltage transmission lines to operate under harsher thermal constraints. Electrical equipment naturally generates its own internal heat while carrying a heavy load. When the outside air is already hovering around 46 degrees Celsius, the infrastructure has a much harder time rejecting that internal heat into the atmosphere. Transformers have to work harder to keep their oil and winding temperatures within safe limits. This creates a brutal double squeeze on the power system during the absolute worst moments of the summer, exactly when millions of air conditioners are demanding the maximum possible amount of electricity. The grid must deliver that power while fighting reduced thermal efficiency. The hotter the afternoon becomes, the harder the chillers have to work. And the harder the chillers work, the more current must flow through cables and substations that are already baking in the sun. Under these extreme conditions, the physical tolerance of the infrastructure narrows. The hotter it gets, the more valuable every single remaining megawatt of operating margin becomes. This dual pressure forces a very uncomfortable question. What actually happens when a city whose buildings rely on continuous mechanical cooling loses that cooling, even temporarily? Imagine a localized power failure striking a fully occupied luxury tower on a late August afternoon. When the electricity disappears, the most critical visual change is not the darkness. It is the sudden silence of the air vent. The heavy fans slowly spin down and stop. The chilled water pumps deep inside the mechanical rooms shut off. The entire mechanical cooling process instantly ceases. In a climate-controlled desert city, the most dangerous consequence of losing power is not simply that the lights go out or the elevators pause. The real consequence is that the artificial indoor environment immediately begins losing the machinery required to maintain it. Without continuous heat rejection, the solar radiation striking the glass facade begins to rapidly alter the temperature inside the enclosed spaces. That creeping heat does not stay confined to one room. It spreads through the tower, into the hotel lobbies, across the massive shopping malls, and throughout the commercial districts. The glass towers were designed with the assumption that the cold air would never stop flowing. They are sealed environments that offer almost no natural ventilation to fall back on. When mechanical cooling becomes this deeply essential to the physical survival of the building, a fundamental shift takes place. Is electricity still merely a basic public utility, or has it become a critical life support infrastructure for the entire urban environment? The immediate response to this vulnerability is usually financial. Dubai is one of the wealthiest urban centers on the planet. Capital can absolutely buy more capacity to defend the grid. Money can build larger substations, lay thicker high-voltage lines, and construct massive district cooling plants. But wealth cannot repeal the laws of thermodynamics. No matter how much money is poured into the transmission network, it cannot create an August afternoon that no longer requires intensive mechanical cooling. Capital simply allows the city to build a larger machine. And rather than permanently solving the heat trap, this limitless wealth fuels an endless infrastructure treadmill. Watch the visual rhythm of how the city actually expands in real time. Engineers construct a new electrical substation to support a massive new climate-controlled development. Developers then build millions of additional square meters of enclosed floor space. All of that new enclosed space instantly creates massive future cooling requirements, which pushes the baseline electrical demand higher during the extreme summer peak. And to safely handle that higher peak, engineers must immediately begin planning the next layer of electrical infrastructure. Expansion successfully solves yesterday's physical constraint, only to immediately create tomorrow's additional load. The new substation enables the new tower, and the new tower demands the next substation. There is no final state where the electrical grid is permanently finished, because the real estate development never stops. The city can certainly continue running faster. It can deploy more capital and hire more engineers, but the treadmill it is running on is moving at the exact same speed. This constant acceleration forces us to re-examine what we actually mean when we talk about a system being vulnerable. There is a critical difference between reliability and independence. A heavily engineered power grid can function extremely reliably for years without a single major interruption. But if an entire urban environment becomes completely unable to function normally without that system, its indispensability itself becomes the vulnerability. The real threat to Dubai is not that a massive blackout is imminent or that the power grid is currently collapsing. The utility authority has proven its ability to keep the lights on and the water chilled. The true threat is what happens to an urban environment when failure is simply no longer an acceptable option. Luxury is strictly marketed as an effortless experience. Perfectly transparent glass towers, brilliantly illuminated shopping malls, and quiet, aggressively cooled hotel lobbies are designed to feel entirely separated from the harsh reality outside. But the more effortless those spaces appear, the more continuous and powerful the machinery operating behind them must become. The more invisible the infrastructure feels, the less visible the dependency becomes. Tourists do not see the massive pumps moving millions of gallons of chilled water. They do not hear the heavy transformers stepping down high-voltage power in the middle of August. They only feel the cold air pushing through the vent. But once the city is viewed through the lens of this massive hidden machine, the reality of the environment completely shifts. The real extreme heat energy trap is no longer simply outside in the desert. It is hidden inside the very loop that makes the city possible. The extreme desert heat forces the buildings to require intensive mechanical cooling. That mechanical cooling requires a massive and continuous supply of electricity. To deliver that electricity, the transmission and generation infrastructure must aggressively expand. That infrastructure expansion makes even more climate-controlled development possible in one of the harshest environments on Earth. And every new square meter of that space requires even more mechanical cooling, sending the thermal demand directly back into the electrical system. Dubai did not actually remove the extreme heat from the city. It created an incredibly complex, highly energy-intensive machine capable of continuously holding much of that heat outside the spaces where people live, sleep, and work. The city's apparent victory over the desert heat completely exposes its absolute dependence on the electrical systems required to maintain that victory. The battle against the climate has not ended. It has simply become permanent infrastructure. Every chilled room, every cold lobby, and every indoor attraction is an active front line in a continuous thermal war. The utility grid is the supply line for that war, and it can never be allowed to falter. The system must continue to operate every single day, drawing power and rejecting heat, just to maintain the baseline habitability of the structures. Dubai did not make extreme heat disappear. It built a machine that cannot stop pushing it away. Look at the illuminated Dubai skyline late at night. The city appears most powerful and secure when the machinery completely fades into the background. But behind the quiet luxury of an empty shopping mall or a perfectly chilled apartment, the heavy industrial work never actually stops. Water is still being relentlessly pumped through miles of insulated pipes. Massive chillers are still actively rejecting heat into the warm night air. Transformers are still carrying heavy electrical loads to keep the system pressurized. And the artificial indoor climate is still being strictly maintained. The visible product is limitless luxury. The invisible requirement is absolute dependency. Because the desert did not disappear, it remains waiting on the other side of the glass. Which leaves us with a fundamental question about the future of extreme urban environments. Which is the better definition of true urban resilience? Is it having enough heavy infrastructure to continuously fight extreme heat? Or is it designing a city that requires significantly less machinery to survive it? This video is produced for educational and analytical purposes, examining urban infrastructure and climate adaptation based on publicly available historical data and engineering principles. It does not predict specific future operational failures and should not be used as professional engineering, architectural, or investment advice. How would you define a resilient city in an era of rising global temperatures? Share your perspective in the comments below. If you found this investigation valuable, subscribe to the channel as we continue examining the hidden systems that keep the modern world running.